Better? Yeah. Okay, good. Okay, so let me go to the point of my talk. I'd like to discuss mainly large deviation results, and I'm saying that I'm considering large deviation for XXX spin chain. What I really mean are the stochastic processes associated to spin chains of symmetric type. Okay, so my talk is that's the plan, and I will spend actually a bit, almost half of my time for the first point to discuss a series of models, and I will also mention some results related to those models. And then I'll go to the main point of the talk, that is a large deviation result in path space. So this is joint work with Tomohiro Sasamoto, and I will explain why we want to consider this new type of large deviation and hopefully argue how they can be useful. And I will have some comments and if time permits, some details of proof. And I'll show a concrete application of this, at least I mentioned the result in ongoing work with Kiron Malik and Ayate Suda and Tomohiro as well, for the calculation of the generating function of the current in a setup of the infinite line. Okay, so let's start with this model description. And of course, starting point, it has been already recalled in some of the previous talk, so that we are all on the same page, is the exclusion process. So it's a Markov process with exponential clock associated to each of the particles. Say at rate 1, they try to jump, and they do it if there is space on the site where they want to jump. The typical setup is with one particle per site. And yeah, this is it has been a prototype and pivotal for several results. Starting from the matrix product ansatz solution, which is rooted in the fact that for spin 1/2 the model is integrable. Maybe, okay, this is super well known, but to better place what comes after, let me recall how this is, the process, exclusion process is related to a stochastic realization of the SU2 Lie algebra. This is very well known, and maybe the interesting point is that this is true for not only for spin 1/2, but generically for 2s plus 1 dimensional representation. S is the spin which labels the representation, and if you then consider this representation with matrices of the creation, annihilation, and number operator for the SU2 algebra, and then you look at the coproduct of the Casimir, I mean the density of the XXX spin chain, then you obtain a partial exclusion process. So now on each site you allow up to 2s particle, and you move a particle from say site 1 to site 2, depending on how many particles you have at the departure site and how many hole you have in the arrival site. And this nicely generalized for exclusion, standard exclusion, you have as a reversible measure a product of Bernoulli. Here you have a product of binomial. Okay, and just to quote few, how to say, nowadays canonical results about large deviations. So of course it was the playground for macroscopic fluctuation theory. There was this prediction from macroscopic fluctuation theory for the at stationarity, a large deviation of the density profile, which typically is linear. If you want to observe something different, the cost is given by this function, and indeed this agrees with what comes out from the matrix product ansatz when for the macroscopic fluctuation theory you specify to the diffusivity equal to 1 and the mobility equal to rho 1 minus rho. Similarly, if we look at large deviation of current in this setup on Z with step initial condition, so we start from the left of the origin with a product Bernoulli with some density rho left, and the right product of Bernoulli with some density rho right. Then the microscopic computation for the cumulant generating function of the current, which is given by this explicit expression, they again agree with what one obtains from the macroscopic fluctuation by solving the macroscopic fluctuation theory equation, as it was done recently. And this also let emerge the connection to integrable classical system, which is at the base of this new solution. Okay, so this is a very familiar setup. Now I start the question now about other models. And a good starting point is the KMP process, which was introduced by Kipnis, Marchioro, and Enrico Presutti. And I mean, it's a model, but to me, it's even more than a model. I mean, there is a program there that is to compute the stationary measure. So they were trying to go beyond exclusion in some sense, and now they have at each site a continuous variable, which you can think like the energy of oscillators. But the dynamic is it's purely stochastic, so the energy is redistributed in some microcanonical way, meaning that the total energy of each couple is conserved. And yeah, they developed an approach, which in modern term we call a duality, by which the description of the stationary measure of the non-equilibrium steady state is essentially given by the properties of the dual process. Let me explain this in some detail. So this is the process. At each site we have energy, and we redistribute uniformly the fraction u of the total we give to site I, and the remaining fraction to site I plus 1. And then we have this dual. This was already, of course, noticed for exclusion, the work of Herbert. And here, there are additional aspects, meaning that the continuous process becomes discrete in the dual, becomes again a particle process. And the other crucial point is that the boundaries of the original process, which inject and remove energy by trying to realize some Gibbs distribution at the boundary, they are replaced by absorbing boundaries in the dual. So to study the original process, actually, if you use the dual process in the long time limit, you will have to know how many particles, dual particles, are absorbed to the right and how many are absorbed to the left. Once they reach this extra site, 0 and n plus 1, they stay there forever. Okay, so this is a bit more formal, what I said in words. So the generator of the process, which has this structure, the bulk part and the boundary part. At the boundary, you thermalize with some temperature T left and T right, and in the bulk, for each couple, you redistribute. That's the original process. The dual, the redistribution rule occurs now at the level of number of particles. So, and again, it's uniform. If you have eta I particle and eta I plus 1, the total, it's this, and you redistribute. And at the boundary, from site 1, you put particle to site 0. And from site n, you put particle to site n plus 1. And the precise statement that they made is that if you look at essentially correlation function, but properly chosen one, so you see this eta factorial, this is crucial to recover the fact that the evolution of this correlation function, which will be closed, the hierarchy of correlation function, the couple, but when you take this coefficient and precisely that one, you can see the evolution of correlation function as the evolution of the indices of those correlation functions. This is the dual process. And therefore, you get this equality for expectation. So here on the left, you have an equality for the original process, x, started from this configuration little x, which you can study by considering the dual process eta started from a fixed configuration eta. And in particular, the consequences of this when you take t to infinity is that the expectation of these moments with this coefficient are a polynomial in the parameter t left and t right of the model, where the coefficients are precisely the absorption probabilities. So you start with eta particle at time 0, and you want k of them absorbed in the extra site 0, and the remaining one absorbed in the n+1 extra site. Okay, so the task is to compute those probabilities. Good. Before going on, maybe since this property and this approach then has been found on several other models, maybe it's good to ask why is that we have this duality property and this dual absorbing process. So a proposal for that is the following. I mean, it's convenient, going back to already the remark at the very beginning, to have an algebraic approach where the generator of the process is recognized as an element, as an abstract element, actually as the realization of an abstract element which lives in the product, in the space of combination of product of the generator of some algebra. This is the universal enveloping algebra of a Lie algebra. And then you look at two representations, and in these two representations, you obtain the generator of the original process and of the dual process. But this, the important point is that this starts at the level of the algebra. So for the generator of the algebra, which you then combine in different ways to produce generator of processes. But once you have the duality at the level of algebra, this will be propagated for the processes. And then you can start to classify processes associated to algebras. And yeah, maybe I take the occasion to advertise, we are finishing this monograph with Frank Redig, where we explain this approach. But to be concrete, and with reference to the KMP process that I was discussing, what is this abstract object? Well, it's an innocuous, seemingly innocuous modification of the original spin chain that we started from. Essentially the same, but the spins, now they satisfy the SU11, the algebra. So this is a non-compact algebra, and the main difference is this commutation relation. And then the KMP process can be obtained by taking this so-called instantaneous thermalization limit. Let me be more explicit. So for, okay, and please remark here that for exclusion, we said that spin 1/2 is integrable. Integrable here in the sense of Yang-Baxter equation. For KMP, this chain is not integrable for any spin value. So the duality of KMP can be understood by considering two representations of SU11 algebra. So this, the first one here, it's with differential operator. Think of acting on monomial. So this S plus multiplies by X, so increase the degree by 1. S minus decrease the degree by 1, and S0 keeps the degree. And this is a realization of the algebra. Now, if you write the spin chain in this representation, you get a diffusion process, which is the Brownian energy process, which is written here with this drift and this diffusion, whose reversible measure are product of gamma IID. And from here, it's one step to arrive to KMP, because if you consider this limit, this means that you are taking expectation with respect to the stationary state of this Brownian energy process with two sides. And when you have two independent gamma and you fix the sum, because this process will conserve the sum of x1 and x2, for the fraction x1 divided by x1 plus x2, you obtain a beta law with this parameter. In particular, when the spin is 1/2, it's a beta 1,1, which is the uniform law. Okay, that's the KMP redistribution rule. Actually, this provides a generalization of KMP. And similarly, if we now consider a representation with matrices, now they will be infinite dimensional because the algebra is non-compact. They are a realization of the SU11 algebra. And when you look at the spin chain in this representation with matrices, you get this process, which again resemble very much exclusion, but now there is a plus here instead of a minus. So we call it inclusion because the particle indeed, they have a preference to attract each other, to stay on the same side. So this part, it's just a random walk part, but the product eta 1, eta 2 makes it larger, the rate for the particle to be on the same side. Okay, and again, it's very complementary. We move from product of binomial that we had for partial exclusion to product of negative binomial. And when we take the thermalization limit of this particle process, we will recover the dual KMP. Okay, indeed, if we have a product of negative binomial, we fix their sum, they are independent, then the first one is beta binomial with this parameter, and when S is 1/2, that's uniform again. Okay, so this is an example, but as I said, it applies to very many class of example, but the main, you recall this was the duality function in the theorem of Marchiori-Presutti, and you see that this is really the duality function for the duality at the level of the algebra generator. So S plus was the creation operator acting on the number n, and S plus was the multiplication by x here acting on the x variable. Okay, good. So this is the duality perspective, and it is a program, as I said. Since the class of models for which we have duality is very large, then for all this model, we can in principle describe their non-equilibrium steady state by these absorption probabilities of the dual particle. However, and this indeed already led in the paper of Enrico at the very beginning to proof of local equilibrium. That paper was the first derivation of Fourier law in the stationary state for a purely stochastic model. But if you really want to have a closed form expression for the stationary measure, you need to compute these absorption probabilities. Now, the paper of KMP was called Exactly Solvable Models. So I still think that one should maybe interpret that title in the sense that you can really compute this absorption probability, but as of today, this has not been done. Nevertheless, one can apply, I mean, it's a model with this macroscopic in the discrete version coefficient, and therefore one can apply the receipt of MFT and produce, for instance, this prediction for the density large deviation function at stationarity. But strictly speaking, one could not apply MFT to these models, and I will argue why, although the result, of course, is correct. Okay, so next step, I mean, if we really want to run the original program associated to the introduction of KMP model until the end, so here we reverse the logic. Can we identify a model for which we have a structure which is related to integrability, which we then can exploit to compute this absorption probability of the dual? So this is what we did indeed with Rowan Frasek and Orge Kurchan, and what we had to do was to look in the literature for the integrable SU11 the chains with SU11 symmetry, which indeed are well known already in this. Several people work on that from the perspective of theoretical physics and string theory, and they are very elegantly written in terms of the d gamma function. But the problem is that they involve this operator, I don't know how to call it, stylized S, which is defined implicitly from the coproduct of the Casimir. So this is in the tensor product representation that is used to read the process. This is non-diagonal, and therefore you need first to go to the base where the sum of two spins is diagonal, so we have Clebsch-Gordon coefficient, and then you realize of the matrix element of this Hamiltonian. And when you do so, if you employ the stochastic representation, the same one that we used for KMP, we could realize that there is a process. And so indeed, there is a family of process depending on which representation you use. So if you use matrices, this will be what we call the harmonic process. So this is the process where at each site you have how many particles you want, and if you have n particles, you move k of them symmetrically to the right or to the left with rate 1/k. Okay, one particle at rate 1, two particles at rate 1/2, and so on. So it's a redistribution model of particles similar to KMP. I mean, you have a total number of particles here at these two sides, and you redistribute them like in KMP. But the redistribution rule is different, and here it's specifically associated to this rate 1/k for spin 1/2. You can define it for every spin. So for spin, well, let me skip the formal description. For spin S, you will instead have these rates, which looks not so nice for the first time that you look at it, and you will never think of it, but this comes from this abstract form of the Hamiltonian when you go to this representation with matrices. And the name harmonic is justified by the fact that if you sum these elements over K, then this is the diagonal element of the matrix, I mean the holding rate before you make a jump if you wish, and this is related to harmonic number for spin 1/2 and generalized or shifted harmonic number for spin S. So this explains the name. And yeah, so now you are in a good position to formulate the problem. So if we take boundaries parameter which are equal, we are in the equilibrium setup, we have a reversible product measure of negative binomial again, and when they are different, we will have a non-equilibrium steady state which we would like to compute. And yeah, this is what is written here. There is also a representation with differential operator which will give a integrable heat conduction model similar to the original KMP1, and the generator is written here. Essentially, let's look at spin 1/2, so this part is not there. Now we have a continuous version. We have energy X, and we move an amount alpha from site I to site I plus 1 at a rate 1/alpha, rate between quotation. Okay, so for this model, we can run the program and we can explicitly describe the non-equilibrium steady state. So this was done in these two work. In the first one, we computed these absorption probabilities. So if you, like, concrete instance, if you have one dual particle, this will be just one random walk, and it's linear, the probability to be absorbed at left or right in the starting point, so you get the linear profile. If you have two dual particles, you compute the covariance and you get this form, which shows long-range correlation. If you get three dual particles, you compute the third cumulant and you get this form, and so on. You can produce an expression for all these moments, factorial moments, which is a polynomial in the two parameter left and right with explicit coefficients, which looks, I mean, you can start to recognize some structure here. There are partition and so on, but it's still substantially complicated. So the next step was to put these moments into a generating function and computing this generating function, and then everything becomes more transparent. If you do this computation, this is the end result, and you see that there is a blue part and a red part. So the blue part can be recognized as the generating function of a negative binomial random variable, which is written here, with a parameter which is side dependent. And the law of this parameter is this red part, which can be also recognized, and it is the ordered Dirichlet process. So one starts from the Dirichlet process on the simplex, symmetric one, and then starts to sum the coordinate of the process. It's permutation invariant, so you can do it in every order, and you get precisely this density here. So final result is that the generating function, it's an expectation of this conditional expectation. So this means that the law, this invariant law, it's a mixture. So you start from a product of negative binomial, but the parameter of this negative binomial, they are random, then they are distributed with the law of the ordered Dirichlet. Okay, so this we first identified for spin 1/2. It was noticed from the MFT results that this structure could be, was tried for KMP, but it didn't work. Here for this model, it does. And okay, once you have this, you can really, exactly like for the exclusion process, you can now compute for instance, the large deviation function of density as stationarity, and you find a result because you will have the joint large deviation of a product measure, which you can start simply control, and the parameters of the measure whose large deviation are also known. This is order statistics, and it's known. And it's precisely this term here, which comes from the large deviation of order statistics, and this term here is the relative entropy between a product measure with a parameter rho, which is the one that you want to see, or a parameter theta, which is the one that you would have. And this is the same expression of KMP. So this strength, the universality of macroscopic fluctuation theory, because this model, the integrable one, and KMP, they have the same macroscopic coefficient, and therefore they get the same rate function. Okay, maybe I should speed up, but that's a recap of models so far. So we started from exclusion, partial exclusion, which is integrable for spin 1/2. And then by going to non-compact spins, we got family of processes not integrable, inclusion process, blind energy process, as well as integrable one, harmonic process and integrable heat conduction. Now, if we want to go to, this was about the stationary measure, so at stationarity. Now, if we want to come closer to the title of the program, we are going to do some hydrodynamics. Okay, so what is the typical setup? Let's again go back to exclusion, true exclusion. You have an hydrodynamic limit, and then you study large deviation around the hydrodynamic limit. So the hydrodynamic limit for exclusion, you look at the empirical density, and this in the limit will converge to the solution of the heat equation. Okay, in this very precise sense, if you couple with test function initial configuration, which are well approximated by a density rho at time 0, then at every time t, you will have the same approximation with rho t, which solves this equation with this initial condition. Very standard. And then for exclusion, there is this fundamental paper of Kipnis-Solla-Baradan, which formulate in precise term, and it's even constructive, the large deviation principle around the trajectory associated to the solution of the heat equation. So now we look at a generic trajectory, mu, and we introduce this linear functional of a generic trajectory mu, and we have a function g, which are twice differentiable in space and once in time. We introduce this functional with the heat equation, and then in the paper, Kipnis-Solla-Baradan, we have a theorem which formulates the large deviation and the cost starting from a local equilibrium measure, and the cost has a component related to the initial condition, which is standard, the relative entropy, and then there is a dynamical part, which is the functional that I defined here, and this term which contains the mobility rho 1 minus rho, or mu 1 minus mu here. Okay, so this is this is the foundation of development of macroscopic fluctuation theory for exclusion. Now, while hydrodynamic and the proof of hydrodynamic limit, this is super general, and either duality or martingale methods will provide this for a very large class of models. Proving large deviation in path space, this is much more demanding. In particular, there is this crucial point of the super exponential estimate, which is needed to close the equation and replacing multi-point expectation by function of the density, which is not trivial at all to generalize. And this has been, for instance, extended to zero-range models by requiring the assumption of having a finite generating function for the reversible measure, which is finite everywhere, which is not the case for all this class of models that I discussed. For these models, inclusion, Brown energy process, harmonic, integrable heat conduction, EMP, we cannot, we don't know how to extend the proof of Kipnis-Sola-Baradan. So bottom line, we don't have a proof of a large deviation principle for these models. Then what can we do? Okay, so here it's the proposal that we would like to put forward. So the proposal is to split the hydrodynamic limit in two steps. I mean, when you do hydrodynamic, you simultaneously scale space and time diffusively for diffusive system. So our proposal is to, I mean, you can encode in this sentence of Katz, be wise, discretize. So keep the lattice structure. So we scale the time, of course, and also the state space with the spin variable, and then first formulate a large deviation principle on the lattice. Then this avoids all the subtle points which are related to coarse graining and the super exponential estimate. Of course, it's much weaker result, but you eliminate some of the problem. We have the observation that if you, once you have done this, then you do a continuous space limit, you recover the formulas of Kipnis-Sola-Baradan. So this is an indication that in principle, this could be a road to follow. Let me be specific about these results. And again, I focus on the partial exclusion, but exactly, well, not exactly the same. I'll say the different points, but the same strategy works for all the models, including the ones that are not accessible at the hydrodynamic limit level for the large deviation. So we look at a sequence of process. So if we had eta, the partial exclusion process, now we speed up time by s and we divide by s, the state space. So the generator of this scaled process moves mass not by 1, but by 1 over s. Okay? And yeah, the law of large number for this scaled process takes the following form. In the limit s to infinity, the process depending on s is very well approximated by the discrete diffusion on the lattice, the discrete Laplacian. That's what we would naturally expect, no? And this is in this precise sense. And for the large deviation, one can introduce a rate function, which is, okay, that's the boundary term again, and that's form the integral of the Lagrangian, or here better the Hamiltonian, and the Hamiltonian can be computed, and it has this form for exclusion, x1 minus x, and then the term, which indeed is related to tilting of the process. Let me explain in a moment. But the precise statement is that we can prove rigorously a large deviation principle in the sense that for every closed set and for every open set, we have an upper bound and a lower bound with that rate function. For the other processes, the strategy is the same. The law of large number is the same. We will have a different rate function because we will have different Hamiltonians. So for inclusion, actually, again, we go from minus to a plus. That's all that we have to do. For this integrable case, the harmonic one, we have a more substantial modification. In particular, we produce this log 1 minus the scalar product. Now, here is the first comment to understand this log, and this actually comes from a remark of Manas already 2 years ago. So, I mean, one should think of this limit of large spin as a classical limit. And indeed, for the integral case, we had the quantum Hamiltonian in terms of this psi gamma function, and the asymptotic of the psi gamma function is a log. And therefore, not surprisingly, the Hamiltonian that is obtained from the harmonic process can be written, which is integrable quantum. When you go to the limit, you should get the integrable classical Hamiltonian on the lattice, which is the Ishimori spin chain, which is indeed what we find, where the spins are so represented with classical commuting variables satisfying these Poisson brackets. Okay, so this really establishes a close connection between large spin and large deviation. Yeah, I still have a few minutes. Maybe I can give very few details about the proof. I mean, the scheme is clear. So if you want to prove a large deviation result, you have to twist the process in this case, so that the rare event that you would like to see is turned into a typical event. And this is the strategy of already laid down in Kipnis-Sola-Varadan. Here we have to additionally work a bit because we are on the lattice, so we want to obtain first convergence with essentially controlling with Gromval inequality. And then we produce an upper bound and a matching lower bound, as usual, with working with exponential martingale for the upper bound and working with a different representation of the rate function, which is related to relative entropy for the lower bound. Okay, maybe for the tilted process, so we introduce this function h, which tilt the dynamics. And it is precisely chosen, this tilt h, so that the trajectory which are typical for the tilted dynamics, which are those satisfying this flow with this modified vector field f, when h is equal to 0, this disappears and we go back to the discrete Laplace. Okay, okay, so we have to prove that this is the typical behavior for the tilted dynamics, and this, I mean, you introduce martingale, and this allows you to rewrite the process, the tilted process, with the generator plus martingale part, and then you compare it to the one of the deterministic evolution, and you can upper bound the difference between the process and the deterministic evolution in terms of this integral for the vector field f. Then you remark that this f is actually Lipschitz, and therefore you can bound at every time, and then you can take the supremum over time, and you arrive at this inequality. And then you use Gromval inequality, which allows to turn to obtain from an integral inequality of this type an inequality for the final time t. So you, by employing this, you reduce your problem of quantifying the discrepancy between the process and the limit larger than epsilon to a problem for the martingale, because this is the initial condition, which by assumption will have a discrepancy 0, and the problem for the martingale can be treated with quadratic variation, showing that the quadratic variation goes to 0. Okay, so for the upper bound, you have the exponential martingale. I'll stop in 1 minute. And in particular, if you plug this function f you get the exponential martingale precisely with the rate function that I mentioned, and with the Hamiltonian that we want. And then when we employ Markov inequality, we get this upper bound, and since it is an exponential martingale, this is 1, and we are here. And then we optimize this bound by taking this inf. This is for open set. Then when we move from open set to compact set, we have to invert this inf and sup, and therefore we produce the rate function that we want. This is for compact, and then by exponential tightness, you go to closed set. For the lower bound, you have to construct. This was done via Ritz representation theorem in the original Kipnis-Sola-Baradan paper. Here it's simpler. We have to construct to show that the rate function can be represented as the relative entropy between the path space measure of the tilted process and the original one. And this can be done by computation, and by computation, I don't go into details. Yeah, so this is maybe, okay, I stopped by making a summary in words. So the point that I want to make is that, of course, the interesting development related to macroscopic fluctuation theory is extension beyond diffusive system. This we are accumulating several information, but already in the context of even diffusive system, when you leave this assumption of bounded state space and product measure with finite with a generating function which are, sorry, reversible measure with a generating function which is finite everywhere, you don't really know how to establish the large deviation principle, which is the first step that you would like to have before going to macroscopic fluctuation theory. So we proposed this alternative route. Of course, there is conservation of difficulty. The difficulty associated to super exponential estimate must reappear somewhere. But okay, we hope that by this approach we can somehow find an alternative route. And okay, I'll stop, but I just want to show with reference to the computation of the current large deviation, which I'm not discussing. This is ongoing work, but I just wanted to show this scheme that is emerging. So at the continuum, at the level of MFT, we know we have the MFT Hamiltonian and the equation. In spin variable, this is LLE. And by this transformation identified by Chiron, Tomohiro, and they can, and I don't remember the third author, you can map it to Aiken-S system. So for the harmonic process that I discussed, so this large deviation principle of MFT is replaced by this large spin large deviation principle. In terms of spin variable, this is the Ishimori chain. And by gauge transformation, you get the Ablovitz-Ladik here, which is the discrete version of the Aiken-S. So that's a nice parallel of the line above. Okay, thank you for your attention.
Questions? Comments?
So this duality, I mean, can this also be applied to study quantum dynamics, not just to stochastic processes where the generator can be sort of diagonalized, but can you actually apply to really quantum dynamics?
Yeah, so this direction is indeed started to be explored. Not necessarily, I mean, the dual evolution will not be stochastic anymore for the quantum problem, but indeed there are examples. I mean, we formulated it for the quantum SEP of the quantum SEP, and there are also other examples. I think Tomohiro in his talk will illustrate another example. So yes, the answer is positive. It has to be, there is not a general construction as for the classical, and it's more importantly, I mean, it's not clear really how to classify the case where for the dual dynamics, you will really be able to solve it, which what you would like really to have. Already for the quantum set, this was not the case, that the dual dynamics was exactly solved.
Any other questions?
Maybe this is a very tangential question, I think. This is inspired by your remark on the universal enveloping algebra of Lie algebras. So in case of SU2, the universal enveloping algebra has an interpretation in terms of functions on a fuzzy sphere.
In terms of, sorry?
Of functions on a fuzzy sphere. You know, a non-commutative sphere in which the non-commutativity parameter goes like 1 over S, where S is the spin. So in the large S limit, it becomes like the universal enveloping algebra maps to functions on a sphere.
Okay.
So that seems to be a another interesting classical looking model, which can represent some of these. At least a single SU2 spin certainly has that representation.
Okay.
And when you have a spin chain, presumably that can also have some representation.
Okay.
Just a thought.
I'd like to discuss more this. One difficulty that I still have with SU2 is that I cannot construct a sequence of, I mean, as the spin varies, of integrable processes. I mean, you can construct the integrable Hamiltonian again with this psi function, but it's only for spin 1/2 that is really a process. If you already look at spin 1, it's not a process anymore, at least in the base that we usually use. The outside of the diagonal, you get both positive and negative elements. So for the Heisenberg ferromagnet, I mean, the partial exclusion that I discussed, yeah, this is true for every S, but that is integrable only for S1/2. So if you require integrability, you lose the stochastic process. If you keep the stochastic process, you lose integrability as soon as the spin is different than 1/2 for SU2. But yeah, I'd like to discuss more. Yeah.
So for the case of SEP, if you look at there is a Markov duality at microscopic scale, but there is also the analog at the level of the MFT. This was the work of Hawke, and where you make the same transformation and goes to the zero boundary conditions.
Yeah.
Okay. Now, for the other microscopic models that you have, are there any analogs of such transform or dual models at the hydrodynamics through the MFT?
Okay, that's a very good question that we don't know the answer. I suspect yes, and it should be similar to the argument. Again, that argument at the level of macro evolution was essentially using symmetry and the representation with spin variable. So
canonical transformation.
Exactly. But yeah, it would be interesting to really see clearly how you go from how the microscopic duality transformation is tapped into a canonical transformation for the macroscopic dynamics.
Okay, if there are no other questions, let's thank the speaker once more.
Yep.